picture a biological research lab, you probably imagine microscopes and white coats. But modern biology happens primarily inside massive AI data infrastructures. Today, autonomous AI agents, like one called MallClaw, are designed to scrape authoritative databases, such as Uniprot and PubChem. These AI systems can independently evaluate and optimize entirely new drug molecules without human intervention. The exact same data architecture manages our global food supply. Agricultural scientists use AI assistants to maintain massive cloud-hosted repositories of genetically modified organisms, or GMOs. By combining chemical, biological, and agricultural data into unified APIs, developers have connected disparate systems so they can talk to each other seamlessly. Doing so has created a single, massive attack surface. We have digitized the building blocks of life. Whoever controls the data pipeline now controls biological reality. In the past, a hacker would use ransomware to encrypt a target's files and demand money in exchange for the decryption key. AI-driven systems require a completely different approach. The systems we use to engineer life are called biological design tools. Their true value doesn't lie in their executable software code. The real value is their accumulated behavioral knowledge, the millions of hours and dollars spent training the neural networks. Because of that, the modern hacker doesn't want to lock scientists out of the system. Instead, they leave the door wide open and secretly alter the AI's internal logic. Traditional IT security relies heavily on restoring backups to recover from an attack. But a backup is completely useless if the victim doesn't realize the system's core reasoning has already been compromised. So how exactly does a hacker silently corrupt an AI model from the inside out without triggering any alarms? They use a technique called intermittent encryption. Instead of locking the whole file, hackers target and inject random noise into an incredibly minute fraction of the AI model's weight parameters, usually between 0.1 and 1%. This diagram shows a standard file architecture schematic. Because the overall structure and the locked valid header remain perfectly intact, traditional file integrity monitoring tools give the corrupted model a clean bill of health. When researchers load the model to run their tests, the software opens exactly as expected. But because those fractional weights are scrambled, the AI's predictive behavior collapses into absolute nonsense. Top-tier scientists are left actively relying on a multi-million-dollar tool that looks perfectly pristine on the surface, but is entirely broken underneath. Attackers have already moved beyond random corruption to highly targeted manipulation, creating what researchers call integrity ransomware. Instead of scrambling the AI, hackers use a method called backdoor data poisoning. They manipulate the training data sets so that the AI functions perfectly most of the time, but malfunctions on command when a highly specific, hidden trigger is introduced. This animated graph tracks AI model performance. Both the baseline model and the infected model maintain high accuracy on standard benchmark tests. The malicious behavior remains totally dormant until a specific trigger condition is introduced, causing the infected model to violently spike into the error threshold. This creates a new extortion mechanism. The victims aren't paying a ransom to regain access to their data. They are forced to pay simply to restore the reliability and safety of their AI assets. Integrity ransomware effectively holds the scientific method itself hostage. It replaces objective testing and reliable outputs with outcomes manipulated by an unseen attacker. When you connect this silent corruption of AI behavior directly back to the massive agricultural and pharmaceutical data pipelines, the threat scales up rapidly. Take the scenario of an infected AI assistant managing a cloud-hosted GMO database. Hackers can use prompt injection attacks, feeding the AI specifically crafted malicious inputs to hijack its controls. A corrupted AI can then autonomously bypass its own built-in safety filters. It can secretly alter genomic data on the fly or exfiltrate proprietary seed sequences straight into the hands of the attackers. The physical fallout here is severe. These compromised AI designs could embed harmful genetic traits directly into crops, strip away natural pest resistance, or introduce toxic elements into new pharmaceutical drugs. Because scientists inherently trust the AI tools they rely on, these toxic biological traits could propagate covertly through global food and medical supply chains long before anyone detects the anomaly. A digital cybersecurity breach and physical biowarfare are no longer separate concepts. Securing the behavioral integrity of our AI models is now the ultimate front line in defending human life.